The Storm Prediction Center doesn't usually draw risk zones for Los Angeles. They did today. Supercell potential. Possible tornadoes from San Diego through Sacramento. While that's happening, temperatures are running 40 degrees above normal across 10 states. Wisconsin might see thundersnow. The sun is firing flares at solar maximum, and 3 more Pacific systems are queued up, waiting their turn. If this sounds like random chaos, it's not. These events are connected through the jet stream, through gradients, through energy that's been building. We're going to trace the pattern from California's coast to the upper Midwest to the sun itself. Stay with us, because what you're about to discover isn't just forecast. It's physics in motion. Stay with us until the end, because what's unfolding over California right now is only the opening act. The jet stream remains kinked, the pattern still locked in its amplified state, and the conveyor belt of Pacific energy continues feeding systems we haven't even named yet. Emergency managers are preparing, AI models are recalculating, and somewhere over the offshore waters, the next pulse is already spinning up. 3 more systems are stacked behind this one. You'll want to understand what happens when this pattern finally breaks. The Storm Prediction Center just did something they rarely do for Southern California. They drew a risk zone, a marginal risk zone stretching from San Diego all the way north through Los Angeles, past Santa Barbara, and into the Sacramento Valley. If you live anywhere else in the country, you might shrug at that. Marginal risk sounds like nothing. It sounds like meteorologists hedging their bets, playing it safe, covering all possibilities without committing to anything specific. But in Southern California, a marginal risk for severe thunderstorms is meteorologically louder than an enhanced risk in Oklahoma. Because California doesn't do this. It almost never does this. Right now, a strong Pacific low is spinning offshore, and it's creating a tight pressure gradient along the coast. The isobars on the weather maps look like they've been squeezed together by an invisible hand, compressed into narrow bands that indicate rapidly changing pressure over short distances. That means wind, fast wind, sustained wind, the kind of wind that bends palm trees and rattles windows. But it's not just the wind at the surface that matters here. About 1 to 2 miles above your head, invisible to anyone looking up, there's a river of air called the low-level jet, and it's intensifying along the coastline. This jet is moving fast, carrying moisture pulled from the Pacific, carrying energy accumulated over thousands of miles of open ocean, and it's about to collide with something most Californians never think about when they check the weather app on their phone: wind shear. Wind shear is just winds changing speed and direction as you go up in altitude. It sounds simple when you say it like that. It sounds harmless, almost benign. But wind shear is the ingredient that makes storms rotate. Without it, you get rain. Sometimes heavy rain, sometimes flooding rain, but just rain falling from clouds. With it, you get structure, you get organization, you get supercells. And right now, the hodograph curvature along the Southern California coast is favoring mesocyclone development. That's the technical way of saying the atmosphere is preparing to spin. The winds at different altitudes are turning in a way that creates rotation, like invisible gears meshing together in the sky. There's a marine layer hugging the coast right now. That familiar blanket of cool, moist air that Californians know well from June gloom and May gray. But above it, there's a cold core low aloft, a pocket of frigid air sitting thousands of feet up. When cold air sits on top of warm, moist air, the atmosphere destabilizes. It wants to overturn. It wants to convect. The warm air is buoyant, trying to rise. The cold air is dense, trying to sink. The atmosphere becomes top-heavy, unstable, primed for violent mixing. Meteorologists are watching the offshore waters carefully because waterspouts are likely to form out there. Spinning columns of air over the Pacific, visible as dark funnels extending from cloud base to water surface. Some of them might make landfall. Some of them might cross the beach and move inland along the Interstate 5 corridor, transitioning from ocean to land in a matter of minutes. When a waterspout touches land, it becomes a tornado. The physics don't change. The wind speeds don't change. Only the name does. California averages about 10 to 15 tornadoes per year. Most of them are weak, rated EF0 or EF1 on the enhanced Fujita scale, which measures tornado intensity based on damage. Los Angeles gets hit by a tornado roughly once per decade. These aren't the mile-wide monsters that carve through Kansas, leaving foundations scraped clean. They're brief, they're narrow, and they're often over before most people realize what happened. A few broken windows, some downed power lines, maybe a roof torn off. But that doesn't mean they're harmless. Coastal tornado setups are different from tornado alley setups in fundamental ways. In the plains, you have flat land stretching to the horizon, and advance warning measured in hours. Storm chasers can see the supercells developing from 50 miles away. In Southern California, you have hills that block visibility, canyons that funnel winds unpredictably, glass high-rises concentrated in downtown cores, and a population that doesn't grow up learning tornado safety in elementary school. There's no basement culture here. There are no tornado sirens on every street corner wailing their warnings. And then there's the wildfire factor, which complicates everything. The hillsides around Los Angeles are burn scars from recent fires. The vegetation has been stripped away by flames. The soil has been baked, its structure changed, its ability to absorb water compromised. When heavy rain falls on these slopes, the water doesn't soak in the way it would on vegetated terrain. It runs off, fast, faster than most people can imagine. That means flash flooding in the valleys below. That means debris flows, thick slurries of mud, rocks, and charred wood rushing down the canyons at speeds that can flip cars and collapse homes. The hydrology of a burn scar is completely different from normal terrain. Water that would normally take hours to reach the valley can arrive in minutes. It's a ticking clock that most residents don't even know is counting down. While Southern California braces for rotating storms and flooding, the Sierra Nevada is about to get buried under a massive load of snow. Forecasts are calling for 30 to 40 inches of snow above 6,000 feet in elevation. At the highest peaks, isolated totals could reach 8 feet, enough to bury a person twice over. This isn't a single pulse of moisture moving through and moving on. This is a multi-pulse system, a conveyor belt of atmospheric moisture. The initial atmospheric river will arrive first, that corridor of concentrated water vapor in the atmosphere, dumping rain at lower elevations and snow higher up. Then a secondary cold surge will follow behind it, squeezing out even more precipitation as colder air moves in aloft. The mountains will be impassable, the highways will close, the ski resorts will shut down operations, the valleys will be soaked, rivers running high and brown. February timing makes this entire setup even stranger, more anomalous. Severe convective setups in California usually happen in late winter or early spring, March or April, when the seasonal transition is well underway. But this is mid-February. The atmosphere hasn't fully transitioned yet. The jet stream is still volatile, still fighting between winter and spring configurations. The Pacific is still cold, still sending maritime air masses eastward. And yet, here we are, watching the Storm Prediction Center draw risk zones for a state that barely knows what those zones mean. This doesn't mean California is becoming Tornado Alley. It doesn't mean the climate has shifted permanently into some new regime where supercells are common. But it does mean that rare doesn't mean impossible. And when something rare happens in a place unprepared for it, when the infrastructure wasn't built for it and the culture hasn't adapted to it, the consequences ripple outward in ways that amplify the impact. So, why is California doing something it almost never does? What's pushing the atmosphere into this particular configuration at this particular time? The answer isn't just offshore in that spinning Pacific low. It's continental. It's hemispheric. Because while California is spinning up storms and bracing for impacts, the rest of the country is doing something just as strange, just as anomalous. It's warming up. Way up. Far beyond what February is supposed to feel like. The warmth isn't the story. Everyone sees the warmth. They feel it on their skin. They step outside in mid-February, wearing a t-shirt instead of a winter coat, and think, well, this is nice, this is pleasant, maybe winter is finally over. But the warmth is just the surface phenomenon, the visible symptom of something deeper. The real story is the energy being stored behind it, accumulated and waiting. Temperature anomalies right now are running 30 to 40 degrees above average across Iowa, Nebraska, Kansas, Oklahoma, Texas, and South Dakota. 30 to 40 degrees. That's not a mild departure. That's not a warm spell. That's a complete inversion of what February is supposed to be. Chicago is forecast to hit the mid-60s on February 18th, possibly breaking a daily record that stood for decades. Amarillo, Texas might touch the low 80s, temperatures you'd expect in May. The Nebraska Panhandle, which should be sitting in the mid-30s this time of year with frost on the ground and ice on the ponds, is climbing into the 60s and 70s. This is what meteorologists call a false spring, and the name captures it perfectly. The jet stream has arched northward over the central United States, forming a massive ridge of high pressure, an atmospheric dome. The ridge acts like a barrier, trapping warm air underneath and preventing cold air from spilling south out of Canada. On the weather maps, the ridge looks like a mountain range of high pressure extending from Texas to the Canadian border. It's February by the calendar, but it feels like April outside. The grass is greening up in places that should still be brown and dormant. The birds are confused, their migration timing thrown off by temperature cues that don't match the day length. People are washing their cars and planning barbecues and wondering if they should start planting gardens. And beneath all of that surface normalcy, the atmosphere is loading up. Warm air holds more moisture than cold air. That's basic thermodynamics, the Clausius-Clapeyron relation. For every degree Celsius of warming, the atmosphere can hold about 7% more water vapor. More moisture means more latent heat available for release. Latent heat is the energy released when water vapor condenses into liquid droplets or ice crystals. It's the fuel that powers thunderstorms, the hidden energy that gets pumped into updrafts and creates hail and lightning. And right now, Gulf moisture is surging north, riding the southerly flow on the eastern side of that massive ridge. This moisture is unusually far north for mid-February. It's meeting a baroclinic boundary that's tightening from Minnesota down through Iowa, a zone where temperature gradients sharpen. A baroclinic boundary is just a zone where two different air masses meet, where density changes rapidly. On one side, you have warm, humid air from the Gulf of Mexico. On the other side, you have cold, dense, Arctic air sitting stubbornly over Canada, waiting. February thunderstorms in Wisconsin are rare, but they're not physically impossible. The dynamics are there when the pattern aligns. The instability is there when the temperature contrast sharpens. Elevated mixed layers are interacting with the Arctic dome, creating a setup where storms can fire well north of the typical tornado alley zone. These elevated severe storms happen when warm, unstable air rides up and over a cold surface layer, like a car going up a ramp. The storms are disconnected from the ground at first, elevated above the cold air, but they can still produce hail, damaging winds, and occasionally tornadoes if the shear profile is right and if the storms can couple with the surface. False springs aren't new to the climate record. There were intense ones in the late 1990s, in the early 2000s, documented in temperature archives. The jet stream has always had variability. Ridges have always amplified, but magnitude matters here. The bigger the ridge, the warmer the anomaly, the more energy you're storing in the atmospheric system. And when that ridge finally collapses, when the jet stream buckles under its own distortion and allows Arctic air to crash south like a dam breaking, the collision is violent. Warm air doesn't just politely step aside and let the cold pass. It fights. It rises explosively. It convects. The temperature gradient sharpens like a blade being honed, and the atmosphere responds with instability that manifests as storms. This is the loaded gun. The warmth everyone is enjoying is just the gunpowder being packed into the chamber. The trigger is waiting to be pulled, and the jet stream isn't just amplified right now. It's distorted in ways that suggest pattern persistence, that suggest this configuration might last. The waves are exaggerated, the flow is kinked. Meteorologists are watching the upper-level winds carefully, tracking the steering currents, because the pattern doesn't look stable in the way a typical February pattern might be stable. It looks primed. It looks wound up. The question isn't whether something will happen when this pattern breaks. The question is where exactly, and when exactly, and how much energy will be released when it does. Because the atmosphere doesn't store energy indefinitely. It can't. Energy flows. Energy dissipates. Energy transfers from one form to another. And when the atmosphere discharges stored energy, you get storms. You get severe weather. You get the kind of outbreaks that make headlines. So while the fall spring warms the plains and confuses the seasons, while people enjoy the unusual February warmth, another collision is brewing farther north. Snow, ice, and thunder are about to occupy the same sky, a meteorologically bizarre combination that happens only when the atmosphere is truly transitional. This looks like April physics unfolding in mid-February, like the atmosphere has skipped ahead 2 months in its seasonal progression. Widespread snow bands are setting up across the upper Midwest right now, with forecasts calling for 3 to 6 inches across northern North Dakota, Wisconsin, and Minnesota. Isolated pockets could see 8 inches where the heaviest bands set up and stall. The upper peninsula of Michigan is bracing for ice, with accumulations up to 1/4 inch predicted. 1/4 inch doesn't sound like much until you realize that's enough ice to snap power lines and bring down tree branches. Even Boston, far to the east, is expecting a trailing snow event as the system moves through, maybe 2 inches of accumulation. This is winter doing what winter does, the cold season asserting itself. Except it's not just winter happening here. Because south of the snow line, just 100 miles away in some places, there's thunder rumbling through the clouds. The frontal boundary separating these air masses isn't vertical like a wall. It's sloped, tilted, lying at an angle through the atmosphere. Warm, moist air is overrunning cold air at the surface, sliding up and over the dense Arctic dome like a ramp or a wedge being driven into wood. Meteorologists call this theta E advection, and while the term sounds obscure, the concept is straightforward. Theta E is shorthand for equivalent potential temperature, which is just a way of measuring how much heat and moisture are packed into an air parcel. When you advect high theta E air over a cold surface layer, when you push that warm, moist air mass over cold, dense air, you get convective instability. The warm air wants to rise because it's buoyant. The cold air wants to stay put because it's heavy. And when the atmosphere is unstable in this way, it convects. It forms clouds through upward motion. It forms precipitation. Sometimes it forms thunder and lightning. Thunderstorms in February in Wisconsin, Iowa, and Illinois are unusual enough to make meteorologists take notice, but they're documented in the historical record. The physics allow it. You don't need July heat and July humidity to get lightning. You just need instability and lift, the two fundamental ingredients for convection. Right now, there's a jet streak coupling over the Great Lakes, 2 localized maximums of wind speed within the broader jet stream phasing together. A jet streak is like a rapid within a river, a place where the flow accelerates. When 2 jet streaks phase together, When their timing aligns, the lift intensifies dramatically. The atmosphere is being forced upward by the dynamics. Add in lake-enhanced instability from the relatively warm waters of the Great Lakes interacting with the Arctic boundary layer moving over them, and you have all the ingredients for convection, even in February. Thundersnow is possible in the transition zone, that narrow band where precipitation type is marginal, where the temperature profile is right on the edge. Thundersnow happens when the same convective processes that create summer thunderstorms occur within a winter storm structure. The updrafts are there, strong enough to separate electrical charge. The charge separation is there, with ice crystals and graupel colliding in the cloud. The lightning is there, discharging between cloud and ground. But instead of rain falling from the base of the storm, you get heavy snow. It's disorienting when it happens. You hear thunder, that deep rumble that shakes your chest, but you look outside and see snowflakes falling. Your brain doesn't quite know what to do with that information because the sensory inputs don't match your expectations. The temperature gradient is tightening midweek, the contrast between air masses sharpening. The difference between the warm air to the south and the cold air to the north is becoming more pronounced, compressed into a smaller space. A tornado outbreak is unlikely in this pattern. The thermodynamics don't support widespread violent tornadoes. The instability exists, but the freezing levels are too low. The wind profiles aren't optimal. But unlikely isn't zero. Unlikely isn't impossible. There have been February tornadoes in the Midwest before. They're rare events, outliers in the climatology, but they happen. The atmosphere doesn't check the calendar before it decides to rotate. It responds to the conditions present, to the shear and the instability and the lift. So why is the jet stream behaving like this? Why is the ridge so amplified that it's bringing 80-degree weather to Texas in February? Why are the waves so exaggerated that snow and thunder are occupying neighboring counties? This is where the science gets contentious, where consensus breaks down. Some meteorologists point to natural variability, the inherent chaos of the atmospheric system. The jet stream has always meandered since the Earth's atmosphere formed. Rossby waves have always amplified and broken in response to topography and temperature gradients. This is just weather being weather, they argue. Random fluctuations within a complex system. But others point to Arctic amplification, the observation that the Arctic is warming faster than the mid-latitudes, faster than the global average. The temperature difference between the equator and the pole is shrinking. And when that gradient weakens, when the thermal contrast diminishes, the jet stream slows down. It meanders more. It gets stuck in patterns, locked into configurations that can persist for weeks. The debate isn't settled. The data is still coming in. The signal is still being separated from the noise. What is settled is this: the pattern is real. The energy is real. The collisions happening in the atmosphere are real and measurable. And while Earth's air masses slam into each other, creating snow and thunder and confusion, the sun is doing something too. It's at maximum activity in its cycle. And some people are starting to wonder if there's a connection between what's happening 93 million miles away and what's happening in the skies over Wisconsin. Solar Cycle 25 is approaching its peak, nearing the maximum of its 11-year rhythm. The sun operates on this cycle of magnetic activity, waxing and waning in intensity. During solar minimum, the sun is quiet, almost serene. Sunspots are rare, sometimes absent for days. Flares are infrequent. The solar wind flows steadily, but unremarkably. But during solar maximum, the sun becomes restless, active, almost violent. Sunspots cluster across the surface in complex groups. Magnetic field lines twist and tangle like rubber bands being wound too tight. And when they snap, when the tension becomes too great and the magnetic structure reorganizes suddenly, they release energy. Lots of it. more energy than humanity has generated in its entire existence. Active region. 4366 recently produced an X-class solar flare, the most powerful category on the flare scale. X-class flares release the energy equivalent of billions of nuclear weapons. They send electromagnetic radiation across the entire spectrum, screaming outward from the sun at the speed of light, reaching Earth in 8 minutes. This region also fired off multiple M-class flares, which are still significant even though they're a category below X-class. These flares launch coronal mass ejections, or CMEs, which are different from the electromagnetic radiation. CMEs are massive clouds of charged particles, billions of tons of plasma, that race outward from the sun at speeds exceeding 1,000,000 miles per hour. When these CME shockwaves reach Earth, when they slam into our magnetic field like a fist into a pillow, they interact with our magnetosphere. They can trigger geomagnetic storms, disruptions in Earth's magnetic field that can affect satellites, power grids, and radio communications. Minor G1 geomagnetic storm conditions were reported recently after one of these CMEs arrived. Solar wind speeds reached 350 to 500 kilometers per second, faster than normal, but not exceptionally fast. Auroras became visible across the northern United States, much farther south than usual, painting the sky in greens and purples and reds as charged particles collided with atmospheric gases. People in states that rarely see northern lights got to witness them. It was beautiful. It was also a reminder that Earth exists within the sun's sphere of influence. Here's the question everyone wants answered. The question that comes up every time there's a severe weather outbreak during solar maximum. Can solar flares cause tornadoes? The short answer is no. Solar flares do not directly cause tornadoes. There is no physical mechanism by which a burst of electromagnetic radiation from the sun 93 million miles away can spin up a mesocyclone in Oklahoma. The energy scales are completely wrong. The physics don't connect in any direct, causal way. A tornado requires wind shear, instability, lift, and moisture. None of those come from the sun in any immediate sense. But that's the direct answer, the simple answer. The indirect answer is more complicated and more interesting. Solar activity does affect Earth's atmosphere, just not the way most people think. Changes in ultraviolet radiation from the sun can affect stratospheric ozone concentrations. Ozone is a molecule made of 3 oxygen atoms, and it absorbs UV light. When ozone absorbs UV, it converts that radiation into heat. It's a heating mechanism for the stratosphere. When ozone levels change, when UV input changes during the solar cycle, stratospheric temperatures change. And when stratospheric temperatures change, it can modulate the polar vortex. The polar vortex is a band of strong winds that circulates around the Arctic during winter, part of the atmospheric machinery that keeps cold air bottled up near the pole. If the polar vortex weakens or becomes distorted, if it stretches or splits, cold air can spill south. And when cold air spills south while warm air surges north, you get the kind of temperature gradients that fuel severe weather. This is the theoretical pathway that some researchers propose. UV changes affect the stratosphere. Stratospheric changes affect the polar vortex structure. Polar vortex changes affect the jet stream configuration in the troposphere below. Jet stream changes affect surface weather patterns. It's a chain of causation, each link dependent on the one before, and each link is debated within the scientific community. The majority view among atmospheric scientists is that the impact is minimal, that the stratosphere and the troposphere are coupled, but the coupling is weak. Changes up there in the stratosphere don't reliably or predictably translate to changes down here at the surface where we live. The signal gets lost in the noise of natural variability. But there's a minority of researchers who argue the effects are measurable, that the stratospheric pathway is real, even if the signal is small. They point to correlations between solar maxima and certain weather patterns, to statistical analyses that suggest relationships. They suggest the sun's influence is subtle but present. Correlation is not causation. That's the mantra drilled into every science student, the warning against false connections. Just because two things happen at the same time doesn't mean one caused the other. Ice cream sales and drowning deaths both increase in summer, but ice cream doesn't cause drowning. The sun reaches maximum activity every 11 years like clockwork. Severe weather outbreaks happen every year in North America during spring. Sometimes they coincide with solar maximum. Sometimes they don't. Teasing apart natural variability from solar influence is incredibly difficult, perhaps impossible with current data. The data sets are noisy, filled with confounding variables. The mechanisms are complex, involving multiple atmospheric layers and feedback loops. And the honest answer, the scientifically rigorous answer is, we don't know for certain. We have hypotheses that are plausible. We have models that suggest pathways, but we don't have certainty. We don't have proof. What we do have is a pattern in motion on Earth's surface, regardless of what the sun is doing, and with or without the sun's influence, with or without any stratospheric modulation, that pattern appears to be reloading. Because this isn't a single storm system moving through and clearing out. It's a conveyor belt. It's a pattern state. And 3 more systems are stacked up right behind this one, ready to follow the same path. This is not a single storm event. It's a pattern in motion, a configuration that has set up shop and doesn't want to leave. A secondary Pacific shortwave is entering the western trough right now, rotating through the upper level flow. By February 21st, there's minor snow potential as this energy rotates through the Pacific Northwest and Northern Rockies. But the ridge persists over the central United States. The warmth continues. The jet stream stays amplified in the same configuration. This is Rossby wave breaking in slow motion, the atmospheric equivalent of a wave that keeps crashing on the same beach. Rossby waves are planetary scale waves in the jet stream, features so large they can only be seen on hemispheric maps. They're caused by the rotation of the Earth and the uneven heating between the equator and the poles. Fundamental forces that will exist as long as Earth spins and the sun shines. These waves propagate eastward, carrying energy downstream from one region to another. When a wave breaks, when the amplitude becomes too large and the wave overturns like an ocean wave approaching shore, it amplifies. The ridge gets taller, extending farther north. The trough gets deeper, digging farther south. The flow becomes more meridional, a term meaning it runs more north-south than west-east. And once a Rossby wave breaks, once it locks into this amplified state, the pattern can persist for days or even weeks. The atmosphere gets stuck. Right now, energy is propagating downstream from the Pacific jet. The northern stream and the southern stream, 2 branches of the jet that often operate semi-independently, are phasing. They're timing their interactions to maximize impact, like 2 rivers merging and doubling their flow. This is pattern memory, a concept that's hard to grasp but crucial to understanding why weather doesn't just reset after every system. The atmosphere doesn't forget. It remembers its recent configuration. A west coast trough paired with a central ridge favors repeated storm tracks along similar paths. One system follows another along the same corridor. The trough digs in the same place. The ridge pumps warm air north along the same longitude. The energy cycles through like water flowing through a channel. Medium-range models show general agreement on this pattern continuation, a consensus among different modeling systems that all use different physics and different initial conditions. But they're not exact forecasts. Models are probabilistic tools, not crystal balls. They simulate thousands of possible futures based on current conditions and physical laws. They converge on the most likely outcomes, but uncertainty grows with time like a cone spreading outward. A forecast 5 days out is more confident than a forecast 10 days out. which is more confident than a forecast 15 days out. This is why meteorologists speak in terms of probabilities and trends rather than certainties and guarantees. There's a conspiracy theory that pops up every time a major weather event happens, especially when events cluster together. People point to the pattern persistence and ask, is this natural? Or is someone controlling the weather? The claims usually involve cloud seeding, chemtrails streaking across the sky, or government programs like HAARP up in Alaska. So let's address this calmly and factually. Cloud seeding is real. It exists. It's a localized technique where particles like silver iodide are introduced into clouds to enhance precipitation. It's used in some drought-prone regions, trying to squeeze more water out of storms. It's used at ski resorts, trying to maximize snowfall. It can nudge precipitation that was already going to fall, maybe increase totals by 10 or 15%. But it cannot steer jet streams that span continents. It cannot create atmospheric rivers that carry the water, equivalent of the Mississippi River through the air. It cannot amplify Rossby waves. The energy scales are wrong by orders of magnitude. It's like trying to steer an aircraft carrier with a canoe paddle. Geoengineering at a continental scale is not technologically feasible with current methods. The atmosphere is too large, too dynamic, too chaotic. Changing the jet stream would require altering the temperature gradient between the equator and the poles, which would require altering the energy balance of the entire planet. We don't have that capability. Weather modification and climate manipulation are often conflated in these theories, but they're different things. Weather is short-term and localized. What's happening right now in one place. Climate is long-term and global, the average of weather over decades. Myths persist because they offer simple explanations for complex phenomena. They provide a narrative where someone is in control, where events aren't random. The truth is messier. The atmosphere is responding to gradients, to energy imbalances, to physics that doesn't care about human intentions, not to secret programs, not to hidden agendas. But forecasting itself is changing. The tools we use to predict weather are undergoing a revolution that might be as significant as the introduction of satellite imagery or radar. And that revolution involves artificial intelligence learning to read the atmosphere. Artificial intelligence is beginning to outperform traditional ensemble forecasting at medium range, and that sentence would have been dismissed as impossible just 5 years ago. It would have been laughed out of meteorological conferences. For decades, weather prediction has relied on numerical weather prediction models, the gold standard of forecasting, the bedrock upon which every weather app and every evening news forecast is built. These models divide the atmosphere into a three-dimensional grid, creating millions of boxes stacked on top of each other, like an invisible scaffold surrounding the entire planet. They solve the equations of fluid dynamics at each grid point, calculating how air moves, how heat transfers, how moisture changes from one state to another. They're physics-based, through and through, running the actual equations that govern atmospheric behavior. The same fundamental laws that have governed weather since Earth first developed an atmosphere billions of years ago. They're computationally expensive, requiring some of the world's most powerful supercomputers, machines that cost tens of millions of dollars and consume enough electricity to power small cities. They're powerful, capable of predicting weather patterns days in advance with reasonable accuracy, good enough that we trust them to plan our weeks and evacuate populations ahead of hurricanes. But they're also limited by resolution, by computing power, and by our incomplete understanding of small-scale processes, like cloud formation, turbulence, and the exact moment when atmospheric instability tips over into severe convection. Machine learning-based global models started emerging around 2024 and 2025, announced in research papers that caught the forecasting community off guard and sparked immediate debate. These AI models are neural networks trained on decades of atmospheric data, fed every observation we have, every satellite image captured since the weather satellite era began, every weather balloon measurement launched twice daily from stations around the globe. They learn patterns in the data the way a child learns to recognize faces. They learn relationships between variables that human meteorologists might never consciously articulate, but instinctively understand after years of experience. They don't solve equations explicitly the way physics-based models do. They don't calculate the pressure gradient force or the Coriolis effect at each grid point. Instead, they infer the future state of the atmosphere based on what similar past states evolved into. It's pattern recognition on a planetary scale, applied to a chaotic system that humans have been trying to predict since before recorded history. And in some tests, in some weather situations, they're catching pattern shifts earlier than physics-only models. They're seeing the amplification of the ridge days before traditional models show strong signals, recognizing the configuration as similar to past events that led to significant weather. The computational speed is staggering, almost difficult to comprehend when you understand what's being calculated. A traditional model might take 2 to 3 hours to run on a supercomputer, crunching through billions of calculations, solving differential equations at millions of grid points, integrating forward in time step by step. An AI model can generate a forecast in minutes on a standard workstation, maybe even on a laptop sitting on someone's desk. The same forecast that would have required a room-sized supercomputer can now be produced on hardware you could buy at an electronics store. This doesn't mean AI is replacing physics-based models. That's not what's happening, despite what some headlines might suggest. It means they're converging toward each other, each approach learning from the other's strengths. The future of forecasting is hybrid, using both approaches in tandem. Physics provides the foundation, the underlying structure based on conservation laws that can't be violated. Mass is conserved. Energy is conserved. Momentum is conserved. These are non-negotiable constraints. AI provides the pattern recognition, the ability to see configurations in the data that human forecasters or traditional models might miss because they're looking at too many variables simultaneously, or because the pattern is subtle, buried in noise. Together, working in tandem, complementing each other's strengths and compensating for each other's weaknesses, they might identify amplified jet setups weeks in advance rather than days. They might recognize when a ridge is going to amplify and persist rather than just passing through. They might flag false spring patterns before they fully develop, giving forecasters and emergency managers precious additional lead time to prepare communities. Could AI have predicted this false spring earlier? Could it have flagged the California Supercell setup with more lead time, giving emergency managers more time to prepare, allowing them to stage resources, pre-position equipment, warn vulnerable populations days earlier? Maybe. The honest answer is maybe. The technology is still maturing, still in what might be called adolescence. The models are still being refined, still being trained on more data, still being validated against real-world outcomes. But the potential is there, visible on the horizon like distant mountains on a clear day. And with that potential comes ethical implications that we're only beginning to grapple with as a society. If we can see disasters coming earlier, if we can predict severe weather outbreaks a week or 2 weeks in advance, instead of 3 days, do we have a responsibility to act differently? Do we evacuate coastal areas 3 days earlier instead of 1, even though that means more disruption, more economic cost, more inconvenience if the forecast doesn't verify perfectly? Do we pre-position disaster relief supplies based on probabilistic forecasts that carry uncertainty, spending money on scenarios that might not happen? Do we change building codes and insurance policies based on what AI models suggest might happen in 10 or 20 years, restructuring entire industries based on predictions? There's also a risk that comes with any powerful new technology, a danger that accompanies every advance. Overconfidence in AI models could lead to complacency among decision makers and the public. If a model says there's only a 10% chance of severe weather, decision makers might dismiss the threat entirely. 10% sounds small. It sounds unlikely, but 10% isn't zero. 10% means 1 time in 10. That scenario happens. If that 10% scenario verifies, if it actually happens despite the low probability, people still get hurt. Property still gets damaged. Lives still get disrupted. Communities still suffer. Improved prediction doesn't stop disasters from happening. It doesn't change the physics. It doesn't prevent the atmosphere from becoming unstable. It just changes how we prepare for them, how we respond, how we allocate resources, how we communicate risk to populations that may or may not understand probabilistic thinking. And preparation requires trust, a commodity that's increasingly scarce in modern society. Trust in the science behind the models. Trust that the researchers developing these systems are doing rigorous work. Trust in the communicators translating forecasts into warnings. Trust that meteorologists are explaining uncertainty honestly rather than sensationalizing or downplaying. Trust in the institutions issuing those warnings. Trust that the National Weather Service or local emergency management isn't crying wolf or playing politics with public safety. Without trust, the best forecast in the world is just numbers on a screen that people ignore. The definition of normal is shifting beneath our feet like sand on a beach. What used to be rare is becoming less rare. What used to be unprecedented is becoming precedented, added to the historical record, no longer an outlier, but part of the distribution. February tornadoes in California, 80-degree heat in Nebraska, thunder and snow in Wisconsin. These events are still unusual, still noteworthy, but they're happening. AI might help us see the patterns earlier, recognize the configurations faster, give us more lead time before impact. But seeing them doesn't automatically mean we know how to respond. Knowledge doesn't equal action. Prediction doesn't equal prevention. The atmosphere is moving faster than policy can adapt, faster than bureaucracies can update regulations, faster than infrastructure can be upgraded to handle new extremes, faster than culture can shift its assumptions about what weather is normal and what weather is dangerous. We're forecasting better than we ever have in human history. We can see storms forming over the Pacific days before they make landfall. We can predict temperature patterns a week out with reasonable confidence. But we're still struggling to translate forecasts into action, to bridge the gap between knowing something might happen and actually preparing for it to happen. So if AI can see patterns earlier, if it can recognize atmospheric configurations weeks out instead of days, what else are we missing? What other patterns exist in data we haven't looked at closely enough? What other systems are we embedded in that we don't fully understand because we've never had the tools to see them clearly? Because while Earth's jet stream destabilizes and forecasters race to predict it, while storms queue up over the Pacific like aircraft waiting for runway clearance, astronomers are searching for something else entirely. Something massive that might be lurking in our own solar system, in our cosmic backyard. Something hidden in the darkness beyond Neptune, where the sun is just another bright point of light. Something that might reshape our understanding of the solar system we thought we knew. Something that might not even exist at all. Just a ghost in the data. A pattern that looks meaningful, but isn't. The search continues. The models run. And the atmosphere, indifferent to our attempts to understand it, continues responding to gradients we're only beginning to see. While Earth's atmosphere churns and forecasters watch the jet stream distort into configurations that rarely appear on weather maps, astronomers on the other side of the world are hunting for a planet we've never seen. The Planet 9 hypothesis suggests there's a massive object lurking in the outer solar system, somewhere beyond Neptune, orbiting in the cold darkness where the sun is just another bright star among countless others. Estimates put it at 5 to 10 times the mass of Earth, large enough to be classified as an ice giant like Neptune or Uranus, potentially the fifth largest planet in our solar system. It's never been directly observed by human eyes or instruments. No telescope has captured its image. No spacecraft has detected it during flybys. No probe has measured its gravitational field. But its existence is inferred from the clustering of trans-Neptunian object orbits, those distant icy bodies that inhabit the outer reaches of the solar system beyond the orbit of Neptune, in a region so remote that light from the sun takes hours to reach it. These objects have orbital paths that seem statistically unlikely, arranged in patterns that shouldn't exist by random chance. Their orbits aligned in ways that defy probability unless something big is out there, shepherding them with its gravity, organizing their orbits through gravitational influence, the way a cosmic shepherd guides its flock. Infrared surveys in Chile are attempting detection right now, using some of the most sensitive telescopes ever built by humanity. The Vera Rubin Observatory, once fully operational, will scan the southern sky repeatedly, looking for objects that move against the background of stars. The planet, if it exists, would be incredibly faint, barely distinguishable from background stars. It's far from the sun, orbiting in a region where sunlight is weak and warmth is absent, where temperatures hover just above absolute zero. It reflects very little light back toward Earth, making visible light detection nearly impossible. Infrared telescopes are better suited for finding cold objects against the cold background of space, detecting the faint heat signature rather than reflected sunlight. But even with the best instruments humanity has built, machines that cost hundreds of millions of dollars and represent decades of engineering advancement, the search is slow, painstaking, methodical. The volume of space to cover is enormous, a three-dimensional haystack of cosmic proportions. The sky is large when you're looking for something small, when you're trying to find a single dim object among billions of stars and galaxies. The planet, if it's there, is small and dim and hiding in a haystack of stars, camouflaged by the sheer overwhelming number of background objects. Debate within the astronomy community is active and sometimes heated, the kind of scientific disagreement that drives progress. Some researchers are convinced the evidence is compelling, that the orbital clustering of trans-Neptunian objects can't be explained by anything else, that the statistical probability of such alignment happening by chance is vanishingly small. They've run the simulations. They've calculated the odds. The clustering is real, they argue, and it points to something massive out there. Others argue the clustering could be explained by observational bias, by the fact that we've only looked carefully at certain parts of the outer solar system, that our telescopes have only surveyed limited regions of sky thoroughly enough to detect these faint objects. Maybe the clustering is an artifact of where we've looked, rather than evidence of where objects actually are. Or perhaps the clustering could be explained by a different gravitational architecture that doesn't require a ninth planet. Maybe a disk of smaller objects whose combined gravity creates similar effects. The hypothesis remains unconfirmed. The search continues. Telescopes keep scanning. Researchers keep analyzing data. But it raises an interesting question that applies to more than just astronomy, a question that echoes across all of science. How much of our solar system is still unknown? How much have we missed simply because we haven't looked in the right place or with the right instruments? Gravity shapes unseen systems across all scales, from the largest structures in the universe down to the smallest interactions. We infer the presence of dark matter in galaxies not by seeing it directly, not by detecting it with any instrument, but by watching how visible matter moves. Stars orbit galactic centers too fast, given the visible mass we can observe. The orbital speeds don't match what gravity from visible stars and gas should produce. Something invisible must be providing extra gravity, holding galaxies together against their own rotation. We call it dark matter because we don't know what else to call it. We infer the presence of black holes by watching stars orbit around nothing, around empty points in space that bend light and trap everything that crosses their boundaries. We see stars whipping around invisible points at tremendous speeds, accelerated by gravity so strong that not even light can escape. We infer the presence of Planet 9 by watching the orbits of distant objects bend in ways that shouldn't happen unless something massive is pulling on them, unless gravity from an unseen source is subtly influencing their paths over millions of years. Invisible forces shape visible outcomes. This is a fundamental principle of science, the recognition that what we can't see often matters more than what we can. This is a metaphor, not a mechanism. Let's be clear about that. Planet 9, if it exists, has no connection to Earth's weather whatsoever. There is no gravitational link between a distant ice giant billions of miles away and the jet stream flowing over North America. The forces involved operate on completely different scales, separated by orders of magnitude. Gravitational influence from a planet beyond Neptune would be utterly negligible at Earth's distance. But the principle is the same across all these systems, whether we're talking about planets, or weather, or galaxies. Systems are governed by gradients and energy flows. The atmosphere responds to temperature gradients between the equator and the pole. The sun responds to magnetic gradients in its interior, field lines that twist and snap and release energy. The solar system responds to gravitational gradients that shape orbits and determine stability over cosmic timescales. Energy flows from high to low, from hot to cold, from concentrated to dispersed. Systems seek equilibrium, that balanced state where gradients have been eliminated and energy has been evenly distributed. But equilibrium is rarely stable. It's a moving target, a balance point that shifts as conditions change. The jet stream is a gradient-driven system, powered by differences. Warm air at the equator meets cold air at the pole. The temperature contrast creates pressure differences. The rotation of the Earth deflects the flow to the right in the northern hemisphere through the Coriolis effect, that apparent force caused by Earth's spin. The result is a river of wind that circles the globe at mid-latitudes, flowing west to east, separating tropical air from polar air. It's a boundary, a barrier, a zone of transition. When that gradient weakens, when the temperature difference between equator and pole diminishes, the river meanders. It takes a more winding path, developing larger waves and deeper troughs. When it meanders too much, when the waves amplify beyond a certain threshold, it breaks. The flow becomes chaotic. Cold spills south in one location, reaching latitudes it normally never reaches. Warm surges north in another, carrying Gulf moisture into Canada. And in the collision zone between these air masses, in the battleground where warm meets cold, weather happens. Energy is released. Latent heat is liberated. Storms form and intensify. Right now, at this moment in mid-February 2026, February is behaving like April across much of North America. The calendar says one thing, but the atmosphere is doing another. The jet stream is kinked into an exaggerated configuration that meteorologists recognize as unusual even for transitional periods. The ridge is amplified over the central United States, a dome of high pressure extending from Texas to Canada. California is spinning up supercells that the state rarely experiences, storms with rotating updrafts forming along the coast. The plains are warming to temperatures 40 degrees above normal, an anomaly so extreme it would be considered rare in any month. The upper Midwest is colliding snow and thunder in the same weather system, winter and spring physics occupying the same space. 3 more storm systems are stacked behind this one in the Pacific, queued up like aircraft in a holding pattern, waiting their turn to make landfall. The sun is firing flares and launching CMEs toward Earth, releasing magnetic energy built up over months. AI is learning to predict atmospheric behavior faster than traditional methods, recognizing patterns in data that humans might miss. And somewhere beyond Neptune, perhaps 400 to 800 times Earth's distance from the Sun, a planet might be hiding in the darkness, organizing the orbits of distant objects through invisible gravitational influence that takes millions of years to manifest. Systems don't care about calendars. They don't consult dates before deciding how to behave. They respond to imbalance, to gradients, to the presence of energy that wants to flow. Energy doesn't wait for permission or convenient timing. It doesn't schedule itself around human activities. It flows where gradients exist. It discharges when conditions allow. It reorganizes when configurations become unstable. The atmosphere is always moving toward equilibrium, always trying to eliminate temperature differences, but it never quite gets there because the forcing never stops. The sun keeps heating the equator more than the poles every single day. The Earth keeps rotating and deflecting winds through the Coriolis effect. The oceans keep circulating and storing heat in vast currents that span entire basins. And the gradient keeps building, accumulating energy, waiting to discharge. This is how planets work. This is how weather works. This is how everything from galaxies to thunderstorms works, from the largest scales to the smallest. You store energy in a gradient, in a difference between one place and another. You release it when the configuration becomes unstable, when the gradient becomes too steep. You start over. The pattern reloads. The cycle begins again. And somewhere, always, another storm is forming. Another system is organizing. Another imbalance is growing, storing energy that will eventually be released. The cycle continues, indifferent to observation, unconcerned with prediction, responding only to the physics that has governed it since the beginning.